We know that electric charges are conventionally called positive and negative charges, and that like charges repel each other and unlike charges attract each other. However, if the size of charged bodies is very small, but the distance between them is comparatively larger than their sizes, such charged bodies are treated as point charges. Coulomb, C, is the SI unit of electric charge. However, smaller units such as microcoulomb and millicoulomb are also used in electrostatics. Electric charge is a scalar quantity, which has only magnitude but no direction. Hence, the total charge on the body is equal to the algebraic sum of the individual charges given to it. Let us illustrate this with an example. Consider a body carrying a charge, say Q1. We add another charge Q2 to this body. Now, the total charge on the body is the algebraic sum of both charges. That is, total charge Q is equal to Q1 plus Q2. Similarly, if a body carries n number of charges, Q1, Q2, and so on up to Qn, then the total charge on the body Q is equal to Q1 plus Q2 plus Q3 and so on till Qn. While adding the charges, proper signs should be used. A positive sign for a positive charge and a negative sign for a negative charge. We can determine whether a body is charged positively or negatively by finding the algebraic sum of all charges on the body. For example, if a body is given 6 charges, all in Coulomb, say +1, -2, +3, -4, -5, +6, the algebraic sum would be -1 Coulomb, which means it is a negatively charged body. Another property of electric charges is that the total charge in an isolated system is always conserved. When a glass rod is rubbed with a silk cloth, electrons are transferred from the glass rod to the silk cloth. Now, both the glass rod and silk cloth are charged. Here, there is only a transfer of charge taking place. Neither is a new charge created, nor is any charge destroyed. The number of electrons lost by the glass rod is equal to the number of electrons gained by the silk cloth. If we consider the glass rod and silk cloth as an isolated system, then the total charge of this system before and after rubbing remains the same. Therefore, we can conclude that the total charge of an isolated system is always conserved. Similarly, charges are also conserved in natural processes such as the beta decay of a neutron. During the beta decay, a neutron breaks into a proton and an electron, releasing a neutrino. Here, the neutron and neutrino are chargeless particles, while the proton and electron are oppositely charged particles, whose combined net charge is 0. Hence, we observe that the total charge in this process is conserved. The charge on an object is measured as an integral multiple of the basic unit of charge that the proton or electron carries and is denoted by E. This property is called quantization of charge. The magnitude of the basic unit of charge E is approximately equal to 1.6 into 10 raised to power minus 19 coulomb. In an atom, when we refer to the charge on a proton, its value is positive and is referred to as plus E, whereas the value of E for a charge on an electron is negative and is referred to as minus E. Thus, the charge on an object Q is equal to the product of the number of electrons gained or lost by it, N, and the basic unit of charge, E. Now, let us calculate the number of electrons 1 coulomb of negative charge carries. Consider a body possessing a charge Q equal to minus 1 coulomb. Let the number of electrons it has gained to become negatively charged be N. As the charge Q on a body is quantized, we have Q equal to NE, where the basic unit of charge E has a magnitude of 1.6 into 10 power minus 19 coulomb, and Q equal to minus 1 coulomb. Substituting the values of Q and E and simplifying, we have N equal to minus 6.25 into 10 power 18. Here, N is a negative integer, indicating that the body has gained a negative charge. So, we see that 1 coulomb of negative charge contains 6.25 into 10 power 18 electrons, which is a very large number of electrons. In the practical examples we have seen for charging a body, we deal with bodies possessing a charge of about a few microcoulomb. The charge of microcoulomb, that is, 10 to the power of minus 6 coulomb, is very large compared to the basic unit of charge E. When such a microscopic level of charge is involved, the concept of quantization of charge can be ignored, since it has no practical significance, where we say the charge is always added or removed in integral multiples of the basic unit of the charge. Quantization of charge is significant only in the microscopic sense, when the charge possessed is due to a few hundred times the basic unit of charge E, or even less than that. Let us now learn about conductors and insulators. We know that atoms are the basic building blocks of all matter. In an atom, the protons and neutrons are the constituents of the nucleus, while the electrons revolve in orbits around the nucleus. For some materials, generally metals, the electrons in the outermost orbit are loosely bound to the nucleus, and these electrons are called free electrons. These electrons are relatively free to move around the material. Such materials with a large number of free electrons are called conductors, and as such, these materials readily allow the flow of electric current through them and cause very little resistance to the flow of electricity. Metals like copper, nickel, and the human body and earth, etc., are some conductors. Some materials have a very small number of free electrons, and hence offer very high resistance to the flow of electricity through them. Such materials are called insulators. Non-metals such as porcelain, plastic, glass, wood, and nylon are some of the best insulators. It is advisable to wear rubber footwear or gloves or stand on a wooden platform while handling electrical equipment, since they are insulators, and protect us from the harmful effects of the electric current. In the absence of the gloves, any leakage in the current from the electrical equipment is transferred through the body to the earth, and this is known as grounding or earthing. In any household electric circuit, in the mains supply, we see 3 wires, namely live, neutral, and earth. Live and neutral wires carry the electric current, whereas the earth wire is used as a safety mechanism. All earth wires terminate in a thick metal plate buried deep in the earth. When a fault occurs, or the live wire touches the metallic body of an electric instrument, the charge immediately and safely flows into the earth because of the earth connection through the earth wire. This prevents damage to human life and property.